So far, we have discussed many of the advanced tools that are required to solve the complicated circuits. Now, it's time for us to see some of the applications of these complicated circuits. We'll start our discussion by understanding a term known as balanced Wheatstone bridge. For that, I want you all to concentrate on my screen. I have some complicated circuit here. Let's say what will happen in this circuit if I close the key. We have a key here. Let me close this key. Now I have closed the key. As I close the key, we have a battery, and this battery have some potential difference that will generate a current I. Let's say the current is flowing. This time my current is getting divided into two currents, I1 plus I2. Now this I1 again get divided into two more currents. Here I have attached a device that is known as galvanometer. This is known as galvanometer. Why we use galvanometer? So actually galvanometer is a device that you will eventually learn in magnetism. It helps us to understand and to measure very little amount of current. It gets deflected whenever any current will flow through it. Now this also attached with a resistance Rg. It may be the internal resistance of this galvanometer or the wire that we have inside the galvanometer. So I'm taking that resistance in Rg. While changing the values of current, there was a time when I observed that a point will come while if I keep on changing this R1, R2, R3 and R4 randomly, I observed there will be a point when there will be no current. That is, this galvanometer is showing no deflection. What it means? It means that there will be no current flowing in this circuit. Let's try to understand why I am teaching you this and what will be the use of these type of circuits. So first, what we will do, first we'll simply apply the Kirchhoff's voltage law. Every one of us know that how to apply the Kirchhoff's voltage law. Let's apply it for each of the loops. We have two loops here. Let's start with this first loop. I am taking in the clockwise direction. So here you will notice we have the current I1 that is flowing through the resistance R1. While flowing the current through a resistor, what we'll do? We'll observe a potential drop. So I'll write minus I1 multiplied by R1. It's minus I1 multiplied by R1. Now, another current that is Ig is also flowing in the circuit that is passing through the resistance Rg. It's also a potential drop because we are moving through the current in the direction of the current. So we'll get Ig multiplied by small rg plus, now here what we have the resistance R4, but this time as you can see here, this time what is happening? We are going in the opposite direction of the current. That's what we should write. We should write it in the plus way because we will gain some potential. So I2 multiplied by R4 needs to be equals to 0. Let's try to solve it. What we'll get? We'll get I2 R4 is equals to I1 R1 plus Ig Rg. Now this is the first equation. I'll just put it in the box. Let's try to apply the KVL in the second loop as well. Again, I'll take the same direction clockwise. Let's try to put the values. So I have the current here. What will be the value of current in this R2 resistor? I have not mentioned anything here. If you'll closely notice, see, we have the I1 current carrying in this R1 resistance. This I1 current get distributed into two multiple currents that are Ig and one more. This one more we can write I1 minus Ig. Obviously, there will be no current loss. So again, applying the KVL in the second loop, what I should write moving in the direction of current, I'll get the potential drop minus I1 minus Ig multiplied by R3. Now, again, we have the current in this R3 in this direction. That is, we are going in opposite direction of the current flow in R3. And what will be the value of current? Try to understand. I2 is coming here. Ig is coming here. So at this point of time, the current here in I3 or R3, we will get Ig plus this one, I2. So I'll write plus, as we are gaining the potential, Ig plus I2 is nothing but equals to this resistance that I'll write as R3. Here we have actually R2. We'll rub it and we write R2. Now, the third section that we are left with is this element where we have the galvanometer, and we are again going in the opposite direction of the current, as Ig is flowing from up to down. So we will simply write plus Ig multiplied by Rg is equals to 0. Let's try to arrange this equation a little. Let's see what we'll get. We'll get Ig plus I2 multiplied by R3 is equals to R3 plus IGRG is equals to I1 minus Ig divided by multiplied by R2. This we will get from second Kirchhoff's voltage law. Now, as I was telling you earlier, while doing this experiment, suddenly a time come up where this galvanometer shows no deflection. What it means? It means that there will be no current flow in this particular element. That means this Ig needs to be 0. Here also this Ig needs to be 0. Here also this Ig needs to be 0. What it means? It means I2 R3 is equals to I1 R2. This equation we will get, let's say equation 1. Now, similarly, what if I substitute Ig here as well 0? Because for this, we have to substitute Ig 0, as there will be no current we are letting in the galvanometer section. We are observing it as an experiment. So from this, what we will get, let me write it out here, we will get I2 R4 is equals to I1 R1. Now, let me just say this is equation 2, and if I divide these two equations, what I'll get, if you solve, you will simply get R1 upon R4 is equals to R2 upon R3. Well, what it means? This is what we call the condition for balanced Wheatstone bridge. Balanced Wheatstone bridge. Wheatstone bridge. This is the condition for balanced Wheatstone bridge. Now, we are done with the proof of these kind of circuits. Now, let's just quickly see that what will be the actual use of these kind of circuits. These circuits are majorly used to calculate the resistance of any unknown resistance wire. Suppose we have a wire and we don't know its resistance. How can we calculate it? On the application of the same Wheatstone bridge, we have a device known as meter bridge. What we'll do there, I'll tell you. We'll take a wire of 1 meter length. As you can see, this is a wire. This is a wire of 1 meter length. 1 meter length, we have a wire. Let's say that Apple is a good conductor. So Apple is conducting the electricity, and I'm asking you what will be the resistance of that particular Apple. Obviously, we cannot measure it. So we'll measure it with this apparatus. Let me show you how. Suppose we have the resistance here. It's a resistance whose value we already know. And I am saying here that it's X. Now, suppose out of this 1 meter, I have this distance L. What is this distance? This is what we call a null point. Null point means a point where galvanometer shows no deflection. So this is what a point that we call a null point, and here the galvanometer shows no deflection. It's very similar to the previous circuit. What is happening? The current is coming in this direction. It's getting distributed and going in this and this direction. Then we have the galvanometer, so means we have two resistances here, and then they are combined with this galvanometer, and then they again two resistance, this one and this one. So it's exactly same like the Wheatstone bridge. And this particular situation arises when we have the balanced Wheatstone bridge. So for that, let's say I am defining one more property. For the time being, I am calling that property as gamma, and it's nothing but the, let's say, resistance per unit length. Resistance per unit length is gamma. Now, if I have to calculate the resistance of this L length, where I am getting the Wheatstone bridge balanced, what will be the resistance of this L length wire? It's nothing but gamma into L. So resistance of L length wire is nothing but this gamma into L. This is my resistance of this. Now, what will be this distance? It's nothing but obviously 100 minus L, let's say 1 meter, or we can write or we can write 1 minus L, 1 minus L, or we can write 1 minus L. As we are talking in meters, you can also convert it into centimeters. If we are taking the centimeter, this is meter value. If we are taking the centimeter, then it will be nothing but 100 minus L. In many books, you will find that people usually talk about the unit that is centimeter. So let's write the centimeter. Here L is also in centimeters. So the resistance of this 100 minus L, the resistance of this 100 minus L is nothing but gamma multiplied by 100 minus L. This is the resistance of 100 minus L wire. We know this resistance. We have to calculate the resistance of L. Let's say the resistance of Apple is S. Now, how to calculate its value? It's very simple. See, we just simply apply the logic that we did in this previous question. R1 upon R4 equals to R2 upon R3. Means this R1 upon R4 equals to R2 upon R3. Very similarly, X upon resistance of L. So we'll write X, this is a value that I know, X upon this RL is equals to, what we'll write here, this Apple resistance, means this S upon what we have here, the resistance of R100 minus L. R100 minus L. Let's put the values quickly. What we have here, we have gamma L, so we get X upon gamma L, S upon, this is gamma 100 minus L, and we get the value of X as, if I cancel out this gamma, R upon RL upon 100 minus L. In order to calculate the S, X multiply by 100 minus L upon L. So this is the easiest way where we can calculate the resistance of any unknown wire. Let us see one practical example based on this. So suppose now I have the actual values, and again we have to calculate the resistance of this apple here. We'll follow the same logic we have given, that this is a 3 ohm resistance and this is the 40 centimeter length where we'll get the null point. So what I'll do, let's say we have to calculate, so we know that it will be balanced. So it's a simple logic that these 3 upon, here we have 40, this needs to be equals to the S is the resistance of apple, divide by this 100 minus 40, so it's nothing but 60. So if I try to solve, let's say what I'll get S is equals to 6 into 3 upon 4, means 3 is a 6, 4, 9 by 2, and we'll get 4.5 as our final answer. I just shown you a very basic simple example. Well, that's all for this video. I hope you understood the concept behind the balanced Wheatstone Bridge. We'll meet again in another video. Till then, keep learning and keep exploring.